he will speak on generalized Fleming-Viot processes and mutations.
Okay. Thanks for organizing, for inviting me here again. It's a great place. This work on generalized Fleming-Viot process and their properties, some of the properties, was originated here during that program on SPDEs, which was here 2 years ago, 3 years ago. So it's joint work with Julian Bristiki, Durin, and Lorenzo Zambotti. So when we spent some time here, Lorenzo, so we worked on this project and more or less accomplished. It includes, so it's about Fleming-Viot process, which can be characterized by certain SPDs, not very complicated ones, but anyway, one can view them as particular case of SPDs. So, what is Fleming-Viot process? Fleming-Viot process, classical Fleming-Viot process, is described like a process taking values in a space of probability measures, so measures with mass 1 over certain type space E, such that it solves such that the process solves one of characterization is via solution to a martingale problem. You take any test functions over your over space E, integrate it against the process Y, which is a measure, and on the right hand side you get initial measure integrated, integrated with phi, some martingale and some drifter. So the martingale is a continuous martingale, and we specify the quadratic variation we want from this martingale. And this term includes mutation. I'll talk about this. I'll explain what does it mean. And you just, so A is the operator, generator of some semigroup. So when it acts on constants, it gives 0. And you can easily check that if you put 1 here, then the probability mass is preserved. You immediately get 0 quadratic variation. Here from this term, you get 0 from that term. So you start from probability measure, you stay with probability measure. And for the purpose of this talk, well, it's not very important. We'll take E to be the interval 0, 1, the set, the space of types. So the heuristic picture behind this process can be obtained by certain approximations from particle systems. You can imagine that you start from large number of particles of order n, and each particle has its own type, which is from space E. And at a high rate of order n, each particle does the following. It just assumes the type of another particle present in the population, just chooses this type, chooses particle uniformly from other particles and assumes its type. So suppose that for a moment that A is 0, so you don't have this last term. And when it happens, it happens with all the time, so particles just assume, choose the type of the other one, and then you take scale it to get the probability measure get the empirical measure of the process, go to the limit, and in the limit you get this process without this term. You can immediately see from this heuristic description that the number of types present in the population, if you don't have this term, can only decrease. Yeah, since each particle assumes the type of some other particle. So if you have one particle of type A and say other particles of other types, and type A decide to take another type, the type A disappear if it was just only one particle. So the number of types can only decrease, and one can easily check that if you don't have this term, that it doesn't matter where you start, what will be initial distribution of types y0 in your process. When at any positive time, it collapses to the finite number of types in your population, which means that at any positive time, y is just a finite sum of weighted Dirac measures. So you can start from continuous profile, but immediately number of types collapses to a finite number, and your process, in fact, is the sum of weighted Dirac measures. And the whole evolution is just change of the weight of the types present in the population. Now, what does it mean? So, okay, and we didn't talk about this term. Suppose this term is non-trivial. Mutation is there. What does it mean? It means that, okay, that model that we talked about is not good enough, and people said, okay, let's introduce mutation. Mutation means that there is also clock for each particle, and each particle can assume any type available according to some kernel, to some probability distribution. So the clock of particle clicks, and it doesn't do resampling with other particles. It just assumes some other type. And there are different mechanisms different ways of choosing this A. Okay, in many models, you'll see A to be just a Laplacian operator, which means each particle, in some sense, chooses the closest one in the discrete model, closest type in the discrete model, some kind of nearest neighbor type of choosing type. Or you can take any other one. What we'll take so-called, which is called neutral mutation, which means that when the time clicks, each particle, no matter what types it had, if it does mutation, it chooses type uniformly on set E. Okay, just another one. And as you see, so this mutation, so in some sense, goes in the opposite direction from the sampling. It increases number of types in the population. Yeah, that one decreases, and this mechanism increases. And your immediate question, you ask, okay, if you don't have mutation, you have always finite number of types. What happens in the case of when mutation is there? And the answer is when this mutation, so again, it depends a lot on the mutation operator A, but if you take this one of neutral mutation, then you get that in this case you have at most countable number of types in population. Again, it's a sum of Dirac measure, but you may have infinite number of terms. By the way, just before I continue, what I said, this resampling of assuming the type, this part of mechanism, you can also think about the fact that you take two particles in the population, and they randomly decide which type of them they take. If you take two particles, choose randomly two particles A, B from the population, and they assume either type A or either type B. So it's more or less the same. The other way to think about it is that you have each particle have a clock for splitting, for branching into two ones, and at the moment it splits, we choose another particle in the population and kill it. Also gives you the same. So it's different ways of describing the same mechanism of resampling. So, and by the way, so as I said, this depends a lot on the mutation operator. In this talk, we'll talk about this one. If you take A to be Laplacian, everything. So the smoothing properties of Laplacian are very strong, and they overcome this mechanism, and you have continuum number of types in the population if A will be Laplacian, which is not surprising for if you think in terms of SPD, and you take this A to be Laplacian, you know that it smooths the SPD in one-dimensional space, and you will get the continuum number of types. Okay. Now, another characterization of this process. Okay, there is weak uniqueness for solution to this Markov problem. It's well known and well established. Another way to think about this process is to characterize it by SPDE. So we define YTV to be the distribution function of the measure Y. And it turns out you can easily construct the SPD which characterizes this process. You take the distribution function until V, and this is our martingale MTV. So you can easily check by taking quadratic variation that quadratic variation of this stochastic integral will be the same one that you've seen in the martingale problem. It's not difficult. And this one which comes from the resampling. Okay, it's a bit unusual. Recently, this type of characterization by this kind of integrals is very popular in people working on population models. In some, when you in a sense you put auxiliary parameter du here, which says you, in a sense, if you forget about this term, how much in a sense, it says you how much noise you have in the on set V at time t. So this white noise in two parameters, one is time, another is auxiliary u. When you make the integration, you, in a sense, you get the amount of noise in the population, in the model. Dawson Lee showed that there is a unique strong solution for general model, and without mutation, this characterization was given by Rigal and Bertois. Yeah, so I just come back to the properties I've already mentioned. If there is no mutation, there is, and for all time, not necessarily fixed, the number of types is almost sure finite, not necessarily fixed time. And if mutation is strictly positive, and I said that I didn't say this, I said it's most countable, but it's known that at any fixed time there is infinite number of types. Okay, so if you have mutation, no matter what's the strength, theta is the rate, kind of rate with which mutation is coming. No matter what theta is, you have infinite number of types. And you immediately come to the question, okay, maybe there are exceptional times where the number of types still collapses to finite number. And this question was resolved by Schmuland some time ago. What year? It was many years ago, who proved that in fact there is a transition. If theta is small enough, small than some number, if mutation is weak, theta is small, then for sure with probability 1 there are times where just finite number of types are present in population. Or in other words, there is finite number of Dirac measures which build your process. And if theta is greater than constant, then no such times. So the mutation is strong enough. So it's pretty tight result about the this threshold. What we're going to construct to talk about is the so-called generalized Fleming-Viot process. People come to conclusion again that this classical Fleming-Viot we talked about is not okay. There are other models that should be described, and as I said, what we had before is just two particles doing some business. Yeah, they choose the one type. Generalized Fleming-Viot says, okay, you take a lot of them, and they, at some point, when time clicks, they collapse to one type. So many of them, which means in the end you get the previous process, the classical Fleming-Viot is continuous process. This process will be the process with jumps. Okay. It's, so many particles at random times they collapse to some randomly chosen to some type. And we take the particular way of choosing choosing this Fleming-Viot, this generalized Fleming-Viot process, and the way is follows. We define the Poisson point process. So we're going to do it not via martingale problem, we're going to do it via SPDEs, via SPD construction, which is parallel to the white noise construction equation we had before for the classical Fleming-Viot process. So take Poisson point process on this R plus 0101. R plus is time. Okay, the others I'll explain, and this is intensity ds in time. So you have some constant intensity of jumps in time, and you have this measure z 1 minus alpha 1 minus z alpha minus 1. So it's a beta density, and it says you more or less the amount of mass you want to, the amount of particles, amount of mass you want to move to some type in the population. So z is kind of proportion. You say z will be proportion of particles we move to certain site. Okay. So this is a set of types, and you have these, let's say, Dirac measures everywhere. And what you say, let's choose number z. Then we decide where this mass is going. And again, we choose particle uniformly among all the masses we have. And suppose we decide we move here. Then we move here, increase it by z, and then scale everything so that the mass of the whole population stays 1. This is more or less evolution of the process. Okay? This is what M does. It chooses your amount by which you increase certain type, and you need to choose just where you put it. And formally, it gives you this equation. You see, you have the similar function you had before in the white noise formulation, and you have additional parameter du, which has the same role which you have that was in the white noise formulation. It somehow says how much noise you have there. But this z is important. So this is how you choose the mass you move somewhere. Okay? And in previous case, it was just in the domain of central limit theorem, so everything was continuous. Here, you really collapse a lot of particles into one mass. And we just specialize for initial conditions which are uniform. It's not important; you can do it anyway, but here. And this is called generalized alpha Fleming-Viot with neutral mutations. It was considered by Legal, Bertois, Dawson, Okay, so I guess it's the model is clear. By the way, I just wanted to say that the theorem of Schmullen, so it was proved via Dirichlet form technique. So there's another characterization of the process, which in a sense says, let's take all the atoms and we put them in decreasing order, and then you have some kind of infinite number of diffusions. You have a generator for such a process, and there is nice Dirichlet form description of this. And from this, you can derive this theorem. In fact, our method will be completely different. And what we want, in fact, to ask is the analog of Schmullen theorem for this model. It's clear that here also you have infinite number of types at any fixed time. It's easy to show. But the question is, do we have the similar type of results? So depending on theta, you have either have exceptional times where you have finite number of types, or you don't. And the answer is you don't have exceptional times. So no matter what theta you take, you always have infinite number. At any time, you'll have infinite number of types. And I don't know if one can do the Schmuller type of argument here. I don't know. Maybe yes, but I couldn't. We couldn't. When we do the argument, so I'll show you how the proof goes. It's not very complicated, but so in the end, when you do the steps, you will see that the result is more or less clear why it is the case. And the key is relation between Fleming-Viot process and branching process. When you establish this relation, when we see that there exists relation, then the result is really easy, and we'll see how it works. So connection of Fleming-Viot with branching measure-valued process. What I think of? What does it mean? Measure-valued process. First of all, okay, we talk about two Fleming-Viot. One with which is continuous one, which is the first one, and a generalized one. And so the same for branching process. These two big types. So this one is approximation for the first one, for kind of, which is connected to the first one, which says, let's start from many particles, and before we had this resampling, and here we have just birth and death events. Each particles, we have a lot of particles in the beginning, and each particle at a large rate n does branching, and either it has 2 offspring or 0 offspring, which means critical branching, and you also put the immigration with rate n theta dt dx. So which means in time and space you put additional particles here and there in the system uniformly in time and space with rate proportional to theta n. Then you rescale everything by n, and you go with the process. You get this again. You take the site space, the space where all particles live 0, 1. You rescale everything by n, and you get again the measure-valued process, which we call measure-valued process with immigration, and it can be characterized again as a solution to the martingale problem. And you see, so you have again this here 2 terms, martingale and some drift term. This martingale has quadratic correlation like this. It's very similar to the Fleming-Viot. Just in Fleming-Viot, you have also minus something in this term. Here is just the first one. Since the mass is not preserved here, so anyway, it's a bit different. And this one is the immigration. In a certain sense, it's parallel to mutation operator. Okay, we'll see how it works. But you have at any interval 0, v, the process, in a sense, is disconnected from anything else and has this and is described by this equation. So in fact, it's autonomous. So it doesn't know what happens here. You can just build process and on any interval. Okay. And again, you can write the SPD. And again, it's the similar one. Oh, probably I did it wrong. No, it's good. So again, it's a similar one to what we had before. You have 2-parameter white noise, and this one gives you amount of noise in the system. So again, see, if you take the quadratic variation, you immediately get this one. Yeah, so this kind of says, so this says you how much noise you have at time s. It's proportional to the mass of the process up to tau s. And you have this immigration. So mass tends to increase. And again, Thomson-Lee proved that there exists unique strong solution for this equation. Okay, what is the relation between this measure-valued branching and Fleming-Viot? Not this, another one. People who used to work with continuous state branching processes, they used to this type of characterization of the processes via SPD. So via SDs, in fact, in this case. So you, in a sense, you can say, okay, for any interval 0v, my mass, the mass of the process here satisfies the SDE, where at the expense of having square root here, we get rid of one of the parameters in the noise. Okay, you can do this as well. You can check that this quadratic variation is the same like this and the same like this. Just again, it's easy quadratic variation calculation. So you can do it this way. You can also characterize the by SDE. Now again, so the question is, what is the relation? And the relation is very simple. If I have this process, which is again this measure-valued process, and XTV is the distribution function, then I can define the time change based on the total mass of the process. We define this time change, then we rescale process X by its total mass, which gives us the probability measure. Substitute the time changed inverse of t given by t, and one can in fact easily check that this yt is Fleming-Viot with mutation. To my knowledge, it was it's not Perkin 05. It was much earlier. Sorry, it was 91. Sorry. It's in more general case, it's called Perkins disintegration theorem. But you can, again, it's whatever is written here, it's just eta formula. You know this process, you know its semi-martingale decomposition, you do this transformation, and in 15 minutes you can get that yt satisfies the right martingale problem if you do this. Okay? So, which means that in fact our Fleming-Viot process, in the case in the classical case, is just rescaled time-changed branching process. And if you have here atoms, we have here atoms, and whatever we can say about atoms in Fleming-Viot, we can say it via atoms in the branching process, which is the key observation. Since it's just different time, they're just different times. Generalized Fleming-Viot. For generalized Fleming-Viot, we need to build some another continuous measure-valued branching process with branching mechanism, which in fact reflects what is reflected in Fleming-Viot, that you have at certain points you have some particles creating a lot of mass. Since this resampling, when you add the mass, it should be parallel to, in the branching process, to the fact that certain particles at certain point have a lot, gives birth to a lot of mass, and this is reflected in the so-called alpha stable branching process, which on the level of approximating particle systems means exactly what I said. You have branching law in the domain of attraction of alpha stable law. And you say, okay, this process in the end can be characterized, okay, forget about, suppose theta is 0, if you don't have any immigration, then this is the branching process. You have initial mass and something which, some noise, which gives you all these branching events. But we want something which adds the mass, as we had in the classical case we talked a minute ago. And so when alpha equals 2, it's the classical case, we had theta v times t here. Now here you see there is something unfortunate inside the drift term. It's the total mass of the process to the power 2 minus alpha, which means, strictly speaking, it's not in the class of branching processes, since you lose infinite divisibility properties of the branching. A lot of things you still can use in some sense, but strictly speaking, don't have them. And by the way, so since alpha is, we'll take alpha between 1 and 2. So this is non-Lipschitz function. So in a sense, you have here SPDE with some non-Lipschitz function in the drift term. Okay, but this is what one needs. So to get the position. And by the way, so again, as in the previous case, you can write this process maybe in a much simpler form. Maybe people like this more. You can, for any v, you can characterize it as a solution to certain SDE driven by alpha stable process. So yesterday was talk about SDEs driven by alpha stable process, and if you take the total mass process, it's in fact the SDE which depends only on total mass. So just the SDE related to total mass, but it has non-Lipschitz function here, and it has non-Lipschitz function here. Okay. At some point, I will talk about uniqueness or existence to this model, but the question is, okay, remark, if theta equals to 0, it's the classical continuous state branching process. I will call it CSBP. Okay? Okay, so this is the process we're talking about. And the first thing you would like to say that there is exists unique strong solution to this equation until the first time it hits 0. When I say until first time it hits 0, all these problems with the fact that this term is non-Lipschitz go away. We don't care about this. Since until it hits 0, everything is Lipschitz. Okay. So which means, so if you you can use result from Lee-Dawson for the Lipschitz drift to say that everything is unique until it hits 0. If you take v equals 1, since as I said, when v equals 1, everything, all the terms, it depends just on on the total mass process. And then for V less than 1, in fact, the similar proof works, since whenever you establish uniqueness for the total mass, you can somehow treat this term as fixed term. And when you do the usual argument, take the difference of two solutions, then this guy disappears from the difference, and you can proceed with the usual argument of proving uniqueness result. So, which means for V less than 1, you can also get the uniqueness even in the presence of this term. Now you may ask, what happens when after time where solution hits the total mass hits 0? This case is considered in our work, and if I have time, I'll talk about this later. It's in fact non-trivial results are there about pathwise uniqueness of the solution. Okay, but before it hits 0, it's more or less trivial. You may ask whether here, yes, there is correspondence. Yes, you can do the same. You do the time change. Here we had -1 when alpha was 2. Here you have to take 1 minus alpha. You again rescale it, and you say that's Fleming-Viot. Okay. There was paper of 7 authors in 2005, Berkner and many others. People that put Berkner, since it's just the first in terms of alphabet, but there were many people in this project who in fact did all this work in the case of no mutation. They considered also, that we didn't talk about this, about coalescence with multiple collisions. It was all related to that, and they showed, in fact, they proved these disintegration theorems for the case without mutation, and you just need, in fact, again, there is nothing else here apart of the eta formula. At least in this part of the result, you just use the eta formula. You do the eta formula, and when you do the eta formula, you realize that this is in fact the term you need in the immigration to get the to get the Fleming-Viot when you do the eta formula. Yeah, you need to somehow to decide what kind of immigration you take, so that when you do this rescaling of the continuous state branching, you need to see what you should do in order to get the Fleming-Viot. And there you, in fact, you see that this guy appears and says you that it should be there in order to get Fleming-Viot. You cannot just say take the constant immigration theta times t. It won't work since correction is different. Okay. What do I want to talk? Okay. Now, as I said, since we have this connection between Fleming-Viot and this branching process with immigration, non-trivial but still integration, then all the questions about the atoms, how many atoms of Y you have, can be answered in terms of how many atoms of X you have. And only what matters is just the first, all this time change is relevant until the first time the total mass of X is 0. Since this corresponds to the infinite time spent for Fleming-Viot. So we don't, in fact, care for the purpose of this behavior of Fleming-Viot what happens with X after it hits 0. So now what is annoying a little bit is that this immigration, as I said, depends on the total mass of the process. It somehow spoils a little bit the branching properties of the system, and doesn't allow to use directly what results we have for the branching, for the continuous state branching process, or measure valued processes. But you can do easy comparison, and okay, this is the process we are talking about, and let's take T epsilon to be the first time the mass arrives to level epsilon, to small level epsilon. And let's see what happens with this process until this time. And it's clear that this immigration can be bounded below until time t epsilon. And it can be bounded below. You just substitute this lower bound for total mass here, and you get this immigration. Which means it says, okay, your process, our process, this measure variable process can be bound from below by this measure variable process. And if you are going in a direction to show that there is infinite number of atoms in the Fleming-Viot in the process X, this is what we need. We need to bound it from below. If this has infinite number of atoms, and this has infinite number of atoms, and then Fleming-Viot has infinite number of atoms at any time, and no exceptional times. Okay, hope it's clear. We just bound this term from below by this one, and this we can couple then and show that this is larger than that one.
I'm just a little bit confused. I mean, what is the? I mean, you had an immigration process, right?
Yes, this one.
So the population is increasing, and X is the population.
Yes. And now immigration is smaller, which means it's very smaller, which is 1 is below.
So the total population xt of 1, shouldn't that explode rather than go to 0?
No, but it's stochastic process. It may at some point hit 0. It's not exploding in finite time. In mean, it may go up. Yeah, but you still have times it may go down. You can take Brownian motion with drift up, it may hit 0. Eventually, you will see it far away, but it still can hit 0. The Gauss theorem it says if you have a drift, okay, there are such theorems, but one should prove that there are no times it hits 0. It's still possible to hit 0.
So even though this drift would lead to a finite time explosion? Right?
No.
I mean, by
It's
itself,
too small.
wouldn't it?
It's too small since the power is less than 1. Alpha is between 1 and 2.
Alpha is between 1 and 2, sorry. Okay, no, sorry. I take it back. Yeah.
Otherwise, you are right.
Oh.
Otherwise, it will do.
Sorry.
It may do infinite. Sure. Okay. Okay. Good. Okay. What did I do? Okay. Now, okay, we did something. We put some process below our process, below the process with stochastic immigration. We took below some process with constant immigration, and so this allows us to use the techniques from continuous state branching process. We need another piece of information which says which gives representation of the continuous state branching in terms of it's kind of cluster representation. Suppose I have continuous state branching process. So again, it's the same stuff we had before without immigration. And it starts from mass V. Okay? You said take small amount of mass and you start your continuous state branching process. And now you define the kind of excursion law of the process. You rescale the law of the process when V goes to 0 by 1 over V. So you try to start your process from infinitely small mass. Okay. And this gives you Q, which is called excursion law of continuous state branching, or the cluster law. Again, so what you say, okay, let's take the small amount of mass and start here the branching process. Now let the mass go to 0, where you start from. Clearly, if you don't do anything, the process will die immediately. But if you rescale it by 1 over V, in a sense, you see some cluster. You see the law which describes the evolution of the cluster which starts from infinitely small mass. And what is important here is that if I have this law of clusters starting from infinitely small mass, I can define the process with via Poisson point process construction. In a sense, I say if I care only about the total mass, let's say that time goes this way, and I say let's put the marks here, which are given by this Poisson point process with certain intensity, and from here on, we start evolution of infinitely small clusters, which are given, and their law is given by measure Q. Okay? Or if you want this picture, so the time goes up, and you put, and you have a process, okay, this doesn't matter, process with immigration, and you put here points from which evolution of cluster starts. So in fact, you have the immigration of mass, and there are just certain points from which the mass survives. And these points are given by this Poisson law. Okay? And it was proved by Pittman and Yor that if I do this and check what I get the continuous state branching process with immigration B. So it's construction, it's more or less construction without SPDE. You just take Poisson point process and you put excursions. It's excursion construction of continuous state branching. Okay. Why it is important? I just want to summarize. So Fleming-Viot process Y is a simple transformation of process X, which is branching process, with stochastic immigration. This branching process with stochastic immigration can be bounded from below by process Z, which is continuous state branching. And this continuous state branching can be constructed as sum of this excursion. Omega I, the excursion, as I said, starting from all of these points. Okay. Now, if you want to check whether they have infinite number of, if we take exceptional times or don't have exceptional times, we need to have time such that only finite number of masses created here arrived up to time t. This is what you need. To have infinite finite numbers, only finite numbers survive. If there is no exceptional times, and any time you take, you will have infinite number of clusters arriving to these points which were born before. Okay, and so what is important here, we know the law, the excursion law of each cluster, which means we can also show how long it lives in terms of this excursion law. And this is this measure Q says that in fact the density the density law of the lifetime of each cluster is given by this h minus alpha alpha minus 1. And here you can by the way see that this power is minimal when alpha equals 2, which means in effect that okay, we'll see why it's important. And so if I want and what we do, we create the Poisson point process. Now we put these times where the clusters are born, and each of them create its lifetime. This is SI where a cluster is born, it's its lifetime. This is the way where a cluster is born, this is suppose its lifetime. So if you want to have infinite number, or if you want to check there is infinite number of times, it means that there is infinite number of such clusters with the lifetime covering any point t. Otherwise, it doesn't work. So I would like to say it again. Okay. So this is time t, any time t, and you have all the times where the clusters are born. You need, this is how long cluster lives. You need the infinite number of clusters whose lifespan covers point t. Then you have infinite, there are no exceptional times. But this is just Poisson point process, which means it's just Poisson point process calculation. And here it's just the last slide about it. In fact, there is Shep lemma, which says the following. If you have Poisson point process on R plus and R plus, which does exactly what it does here, just a second. It's exactly what it does here. This is better. It gives me 2 minutes more. Okay. Anyway, and it says you put Poisson point processes points here, and each point of Poisson process gives you also some interval. And the question that Shep asked, what are the conditions on Poisson point processes such that you cover all the real line? Which is exactly this question. Just if you cover all the real line, it's more or less immediate that any point is covered by infinite number of intervals, if you cover. And Shep gave exactly strict criterion on what should happen, what should be condition on measure on the Poisson intensity measure pi in order to be covered or not covered. So this integral should diverge, then you are covered. If it's not diverge, you are not covered. And you just take our measure pi dh and calculate this integral. And this measure pi was exactly what I calculated the distribution of the lifetime of each cluster. Then you cover all the real line. And you see that when alpha is between 1 and 2, there's no chance it diverges. No chance it's to converge. It's always infinity, which means you always cover the whole time interval, which means you have infinite number of types at any point. If alpha equals 2, it's tight. You have here a constant. And this constant is in fact this theta, which Schmullen got. Which means when theta is less than 1, it converges, which means you don't cover, you have exceptional time. You have some time, some points which are not covered by all the lives of surviving cluster. And if alpha is greater than 1, no exceptional times these integrals diverge. So it's exactly the reproof of Schmullen result by the Poisson construction of solution, some solution to SPD. Okay, I didn't get to uniqueness, but I guess I should stop here.
Thank you. Are there some questions? No question. Thank you again.